I've talked about lattices in conjunction with ionic compounds, and I've also mentioned lattice energy, but now we're going to more carefully define what those are. So a lattice for an ionic compound looks something like this drawing here. This is for the ionic compound rubidium fluoride, and the same thing can be said for sodium chloride or any other ionic compound. It's not just a single rubidium bonded to a single fluorine, it is a whole lattice of fluoride ions and rubidium ions alternating because they're opposite charges throughout. So it forms a what we call a lattice. All right, and the energy associated with breaking that lattice is the lattice energy. So a definition of lattice energy is the energy needed to break the lattice. And it's given per mole of compound. Okay, so per mole of rubidium fluoride, you have some energy associated with breaking that up into individual ions. And we can talk about trends in lattice energy. Since the lattice is made of charged particles, in this case ions, we can talk about the lattice energy in terms of Coulomb's law, which is given here. And F is the force of the lattice, and K is just a constant, we're not concerned with that. And D on the bottom is the distance between charged particles, which is the ions. So it's the distance between ions. Z1 and Z2 are the charges on the ions. Okay, so we have rubidium plus, we have fluorine minus, so that's 1 plus and 1 minus. So those are the charges on the ions, on the two ions. Okay, and we're not going to do any calculations with this equation, but we do want to understand, we use it to understand trends. Okay, so if you look at this, if your charges are greater, the charges in the numerator, the force of the lattice will be bigger. It'll be a stronger lattice. Whereas if you're, look at the D is on the bottom, and it's squared, so the distance between ions, when that's greater, will be a much, much smaller force of the lattice. So we can say that the force of the lattice is greater for two conditions. One is smaller ions, okay, that's the D, because the ions can only get as close to each other as their size allows. And the second is for higher charges. So if you have, instead of 1 plus and 1 minus ions, if you have a 2 plus ion, for instance, a ionic compound such as magnesium chloride, the magnesium will be 2 plus, and that will be a higher charge for the magnesium. Okay, so we have these two trends, smaller ions, higher charges. And the trends going down a group for size, if you look at group 1, lithium plus on down, where they're all singly charged cations, the size gets bigger as you go down. Okay, for the same reason that the neutral atoms get bigger as they go down a group, you're putting the extra electrons in an outer n level. And in the halogens, which are all 1 minus, the size also gets larger, although it starts larger. Okay, so they still get larger going down a group. So you can look at trends. Iodine would be huge. Okay, you can look at trends on the periodic table and make some predictions about lattice energy. For instance, these here. Look at calcium sulfide and barium sulfide, and you can predict which one will have a larger lattice energy. If you look at your periodic table, barium and calcium are in the same group, and of course we have sulfur bonded to both of them, so that's no difference between them. But calcium is higher in group 2 than barium, so calcium will be smaller, which means it has a smaller ion, so calcium sulfide will have a larger lattice energy. It'll be a stronger lattice than barium sulfide. It'll take more energy to break calcium sulfide than it does to break barium sulfide. All right, and then let's compare calcium sulfide to calcium oxide. Here the cations are the same, but the anions are different. And so you're comparing also two things in a group. Sulfur and oxygen are in the same group, so you can go by size. Oxygen is higher in the periodic table, so it's going to have a smaller ion, so it's going to have a larger lattice energy.
Let's do a few more examples to clarify the concepts. One thing to note is that if you're comparing both a difference in size and charge, is the charge generally is going to dominate over any size considerations. So we can use that information to do a few more problems. Let's compare the lattice energy for lithium fluoride and lithium chloride. The lithiums are obviously the same, and fluoride is a smaller ion than chloride, therefore you expect the fluoride to be smaller and have a larger lattice energy, right? And I can actually show you with numbers. Lithium fluoride is about, this is rounded, 1,000 kilojoules per mole for lattice energy, whereas lithium chloride is only 800. Let's look at the next one. MgO versus MgS. We're just comparing the size of O and S because they're both 2 minus ions. Okay, so the size for the O is smaller, it's higher in the periodic table. The trends going down a group apply to all the groups, not just the ones I showed you. So you can say that MgO has a larger lattice energy, and that's verified by the numbers. 3,800 for MgO versus 3,400 for magnesium sulfide. And you can see that these two numbers for the 2+ cations and anions are much larger than the numbers for the 1+ cations and anions. So now we can compare two that are different in their charges. Sodium oxide and magnesium oxide. Okay, so magnesium is a 2+ ion, sodium is a 1+ ion. The charge is much greater for 2+, okay, twice as big. So MgO is the larger one. We already said MgO is 3,800. Sodium oxide is about 2,700, so much smaller. All right, and finally, the last example is showing a change in both charge and size. You have potassium fluoride, which is a 1+ and a 1- ion, and calcium chloride, which is a 2+ with a 1+. And since charge dominates over size, we're going to go with calcium, and we can look at the numbers to verify that. Potassium fluoride is 800 versus for calcium fluoride it's 2,300.
All right, so now let's practice summing up several things we've talked about in several recent videos and talk about energy of all these changes. So we're going to identify which processes are positive in energy change and which are negative, and look through these, and you should try this yourself. The first one is taking a potassium and ripping an electron off of it, and that energy is referred to as ionization energy, and that is always going to be positive. The second one is putting an electron on an iodine, and that is known as the electron affinity energy, and that for most atoms is negative, and certainly for the halogens it is negative, because they will attain a noble gas configuration by getting an electron, so that's a very favorable energy change. All right, the next one, taking separate ions and forming a lattice, hint hint, is the lattice energy. Whoops. All right, what happened here? So looking at the third one, taking potassium and iodine ions and forming potassium iodine, that would be forming a lattice, so that is the lattice energy. And that will be negative. Okay, that always goes down. It went down in our Born-Haber cycle, and it always goes down. That's forming this lattice is a very favorable energy process. And finally, taking iodine and turning it into two separate iodine atoms, turning it into I and I, is breaking a bond. That is known as the bond energy. And that will always be positive.